Let us now discuss plane strain and plane stress problems. A plane strain problem is a type of mechanical deformation in solid mechanics where a body undergoes deformation under conditions where one dimension is unrestricted. So, in other words, the deformation occurs in a plane and one dimension extends infinitely. This means that the dimension which extends infinitely, there is no strain or deformation in that dimension. Plane strain problem is an approximation problem where length of the structure is much greater than the other dimensions. So in this figure, we can see two structures. One is a dam, another one is a culvert. And in both of these structures, we have got a cross section which is finite, and the longitudinal direction is very big as compared to the dimension of the cross section. So this is a plane strain problem. In the case of plane strain problem, we consider all the stress component and strain component non-zero except the strain in the third direction, which is the longitudinal direction, equal to 0. So strain 3 is equal to 0, gamma 2 3 is equal to 0, and gamma 1 3 is equal to 0. So all the strain components which are in the longer direction or in the longitudinal direction, they are considered 0, and the other strains have got finite values. So from our previous discussion, we have the normal strains and the shear strains defined over here, rewriting this equation in terms of I and j is 1 over E times sigma ij minus nu by E in bracket 3 times sigma h minus sigma ij. Sigma h is the hydrostatic stresses. So in this equation, we can put I is equal to j is equal to 3, and we will get 1 by E sigma 33 minus nu sigma 22 minus nu sigma 11. Sigma 33, according to our assumption of plane strain, is equal to 0. So sigma 33 will come out to be nu times small bracket sigma 22 plus sigma 11. Sigma 33 is the function of x1 and x2. We can again take the same equation, which is epsilon ij is equal to 1 by E sigma ij minus nu by E bracket 3 times sigma h minus sigma ij, and make ij equal to 3, so sigma 33 equal to 0, and work out our hydrostatic stress from this equation, which comes out to be 1 plus nu by 3 small bracket sigma 11 plus sigma 22. Now this hydrostatic stress will be plugged back in equation 2. So we take again equation 2, the terms describing sigma ij is collected together, and we leave the term describing sigma h separately, and then we plug the value of sigma h in the equation. So that's what has been done. Instead of ij, we can write epsilon alpha beta is equal to 1 plus nu by E sigma alpha beta. So this is the term involving sigma alpha beta or sigma ij that has been collected together, and sigma h term has been isolated, and then we can plug the sigma h value as shown over here, and we get epsilon alpha beta is equal to 1 plus nu by E stress alpha beta minus 3 nu by E 1 plus nu by 3 small bracket sigma 11 plus sigma 22. We can now write omega equal to 1 minus nu, mu is equal to g is equal to E by 2 1 plus nu in this epsilon alpha beta equation, and we get 1 by 2 mu big bracket sigma alpha beta minus small bracket 1 minus omega into sigma 11 plus sigma 22 delta alpha beta. This equation has been worked out using these constants in the epsilon alpha beta equation. Similarly, the stress components can be worked out by inverting this equation, and we get sigma alpha beta is equal to 2 mu big bracket epsilon alpha beta plus 1 minus omega divided by 2 omega minus 1 into epsilon 1 1 plus epsilon 2 2 into delta alpha beta. So these are the two equations, the constitutive equation corresponding to plane strain problem.
The second type of problem is the plane stress problem. A plane stress problem is a mechanical deformation scenario in solid mechanics where stress and deformation are assumed to be confined to a particular plane. In contrast to a plane strain problem, in a plane stress problem, the third dimension is unconstrained and experiences no stress. This assumption is often applied in cases where the thickness of the structure component is smaller than its other dimension. So in this figure, we have got a plate which is subjected to in-plane loading, and the cross section of this plate is very small. So this is a plate, it can be a wall, whatever we want to call it, but the thickness is very small as compared to the other dimensions. So therefore, this can be treated as a plane stress problem. In the plane stress condition, the material is considered to be in the state of stress in the plane of interest, but out of plane stresses are neglected. So in this plate, the out of plane stresses, which are having outward drawn normal in the direction of thickness, would be neglected. This simplification is commonly used in the analysis of thin structures such as plates, membranes, and shells, where the effects of bending or stretching in the thickness direction are considered negligible. So, in this thin plate, the forces are applied at the boundary and parallel to the plane of the plate and distributed uniformly over the thickness. The right hand side figure shows the thickness, and we can see that the loads are distributed uniformly over the thickness. So we can say that the stress 3,3 is actually 0, and there can be strain 3,3, which is non-zero, and following this, the shear 2,3 and shear 1,3 will be taken 0. The rest of the stresses, that is stress 1, stress 2, stress 1, 2, strain 1, strain 2, strain 1, 2, they are non-zero. So if we have tau 2, 3 equal to 0, remembering that the first subscript is showing the outward drawn normal corresponding to the plane, and the second subscript is showing the direction of the force which is causing this stress. So tau 2, 3 is 0. So we can write G times gamma equal to 0, G being the modulus of rigidity, times gamma, which is the shear strain, equal to 0. G cannot be 0 for a material, so therefore gamma 2, 3 is also equal to 0. We have derived the general stress and strain equation above. So our stress equation, which is a lambda times epsilon v delta ij plus 2 times mu epsilon ij. So this equation can be rewritten by making the stress in the 3 direction equal to 0. So we are assuming that the outward drawn normal in the 3 direction is towards the thickness. So we have the cross section x1, x2 in plane of the cross section, and x3 is outward drawn normal, which is out of plane, and that is taken as 0. So from there, just making this stress equation equal to 0, We know that mu is equal to g. We have already defined that. Lambda is 3 times the so-called bulk modulus times the Poisson ratio divided by 1 plus nu. And the epsilon v is the volumetric strain, which is epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. So plugging the values of epsilon v in equation A, we get epsilon 3 3, which is the strain in the direction 3, and that is equal to negative of lambda divided by lambda plus 2 mu, small bracket epsilon 1 1 plus epsilon 2 2. This tells us that epsilon is a function, epsilon 3 3 is a function of x1 and x2. In the case of plane strain, we had the stress in 3 3 as a function of x1 and x2. It's clearly different in the case of plane stress. Now, the value of epsilon 3 3 can be plugged in this equation, and we can get the value of epsilon v also. So that comes out to be 2 times mu divided by lambda plus 2 mu, and in small bracket epsilon 1 1 plus epsilon 2 2. So this is our value of epsilon v. Now we rewrite the general equation, which is sigma ij is equal to lambda epsilon v delta ij plus 2 mu epsilon ij. We write this equation in generic form by plugging the epsilon v value, which we just found. Similar to the plane strain problem, we write this equation in epsilon alpha beta. We can write in ij or any other subscript, so it's just symbolic. So sigma alpha beta is equal to 2 times lambda mu divided by lambda plus 2 mu, small bracket epsilon 1 1 plus epsilon 2 2. So we have plugged in the epsilon v value, which we worked out, and that was worked out from the stress 3 3 equal to 0 in equation A. So times delta alpha beta is equal to 2 mu epsilon alpha beta. Now, similar to the strain formulation where we introduce omega as 1 plus nu, over here we introduce a new constant omega equal to 1 by 1 plus nu. The main idea is to get the stress and strain equation similar, the only difference being in omega, so that we can use our stress strain equation in any problem, work out the solve the problem. In the end, correspondingly, we plug the values of omega. In the case of plane stress problem, we define omega equal to 1 by 1 plus nu. Mu equal to g is the same, e by 2 1 plus nu, and from there we can rewrite this stress equation, which comes out to be 2 times mu big bracket epsilon alpha beta plus 1 minus mu 1 minus omega divided by 2 omega minus 1 epsilon 1 1 plus epsilon 2 2 delta alpha beta. From here we can work out the strain alpha beta, which is equal to 1 by 2 mu big bracket sigma alpha beta minus small bracket 1 minus omega small bracket stress 1 1 plus stress 2 2 delta alpha beta. Please note that the stress equation has got lambda and mu. Lambda we defined earlier as 3b nu divided by 1 plus nu, and our b is equal to b, which is the bulk modulus, is equal to lambda plus 2 mu by 3. From here we can bring omega into the definition of these constants, and our omega would be 1 by 1 plus nu, and that's how we change it to the stress and strain problem in omega and mu. This is similar to what we did previously. So in the end, we'll find that the stress and strain formulations for both plane stress and plane strain are in the same shape, the difference being in omega. For plane strain, we have got omega equal to 1 minus nu, and for plane stress, we have omega equal to 1 by 1 plus nu. In the case of plane strain problem, we have got a strain in the longitudinal direction for a structure equal to zero. So we gave the example of a dam and a culvert whose longitudinal x3 direction is considered to be zero. Therefore, the strain was taken equal to zero, and all the shear strains in the same direction were considered zero. In plane stress problem, the longitudinal direction was very small. The thickness was very small as compared to the other dimensions. So we took stresses in the third direction equal to zero. So these are the two major assumptions which we can apply in the case of our advanced structure mechanics problems, and we can simplify our calculations. They will give us reasonably good answer provided we apply it appropriately. So we come back to our boundary value problem. We will now try to work out the governing differential equations for both the plane stress and plane strain problem. And from there onwards, we will stick to plane stress, plane strain problem examples. The next step would be to get the equilibrium equation for the plane stress and plane strain problem. So reminding ourselves of the equilibrium, we in a 3D orthogonal Cartesian system, we derived earlier the differential equation of equilibrium, and that came out to be these three equations. So a partial sigma 1 by partial x1 plus partial sigma 1 2 by partial x2 plus partial sigma 1 3 by partial x3 plus x1 equal to 0. And then similarly partial sigma 2 1 by partial x1 plus partial sigma 2 2 by partial x2 plus partial sigma 2 3 by partial x3 plus x2 equal to 0. The third one is partial sigma 3 1 by partial x1 plus partial sigma 3 2 by partial x2 plus partial sigma 3 3 by partial x3 plus x3 equal to 0. x1, x2, x3 were the body forces in the three directions. Partial sigma portion can also be written as divergence of sigma. So we have already done the divergence. In the mathematical preliminaries, we worked out the divergence of a vector field as partial v by partial x1 plus partial v by partial x2 by plus partial v by partial x3. So this was the divergence equation which we derived in mathematical preliminaries. So rewriting these three equations and now converting them into plane stress or plane strain problem. Automatically, the third equation will become 0, so we can struck it off. Whatever is in the outward drawn normal along the x3 direction will be omitted. So these two will be omitted, and we are left with the first two terms of the first equation plus the body force in x1, and the first two terms of the second equation plus the body force in the x2 direction. We can also write this partial differential as sigma 1 1 comma 1, which means that this variable is getting partially differentiated with respect to x1. Similarly, the second term is differentiated with respect to x2. So this is just a short form of writing these partial differential equations. So we are left with two equations. These two are applicable for both plane strain and plane stress problem. Now, finally, we will discuss compatibility. So essentially, we are trying to apply the boundary value problems onto our plane stress and plane strain problems. So all these governing differential equations have to incorporate the plane stress and plane strain conditions. So the last one, which is the constitutive equation that we already derived, we have discussed the equilibrium. Now we have to do the compatibility. So I showed you this figure. We approach the problem depending whether it's a displacement formulation or a stress formulation. And all the equations are now converted into plane stress, plane strain, except the compatibility. So let us have some discussion about the compatibility. We have derived the compatibility equations previously for Cartesian coordinate system. So in the compatibility condition, we discussed that if we have a known strain field, how would we make sure that the displacements are compatible with the strain fields, and we derived 6 equations. And let us rewrite these 6 equations again. So it's the same equations which are written over here, 6 in number. 3 equations are related to the axial strains and 3 with the shear strains. In compatibility, for plane stress and plane strain, the most relevant equation is the first one, which is relating the strains in x1, x2 direction with each other. So remembering the x1 and x2 axes are the most relevant in both the plane stress and plane strain problems. So therefore, we consider only equation A, and we rather omit the other equation, but we have to provide some sound justification for omitting it. In some places, we will see that they become automatically cancelled out. And in some cases, we force them to zero with some error. So this is just to ease our calculations. So let us now discuss the first equation, which is partial 2 times epsilon 1 by partial x 2 power 2 plus partial 2 times epsilon 2 by partial x1 square is equal to 2 times partial 2 epsilon 1 by partial x1 partial x2. This is the equation which we will be satisfying for both plane stress and plane strain problem. Let us see how can we get this equation running. So we write our epsilon 1 in omega form, 1 by 2 mu divided by sigma 1 minus small bracket 1 minus omega into epsilon 1 plus epsilon 2 both in bracket. Then this can also be written as 1 by 2 mu. So just doing some algebra, and we get omega sigma 1 minus 1 minus omega epsilon 2. Epsilon 2 similarly comes out to be 1 by 2 mu omega sigma 2 minus 1 minus omega small bracket sigma epsilon 1 is 1 by 2 mu sigma 1 epsilon 1 is 1 by 2 g is equal to mu, as we discussed previously, and times sigma 1 So that is, these 3 equations are rewritten. Now we can invoke the compatibility, plug the values in the compatibility equation, which is equation A, and we get omega sigma 1 comma 2, which means that the sigma 1 is partially differentiated twice with respect to x2 minus 1 minus omega small bracket times sigma 2 is twice differentiated with x2. This we get by differentiating epsilon 1 equation twice, and we have the second term, which is epsilon 2 differentiated twice with respect to x1, and that we can perform on this second equation. So the second big bracket has got sigma 2 differentiated twice with respect to x1, and the 1 minus omega sigma 1 is differentiated twice with respect to x1, and then minus 2 times sigma 1 comma 1 Now we have got the equilibrium equations. We already discussed, we reduced the equilibrium equation into 2. We differentiate the first equilibrium equation with respect to 1 and the second equilibrium equation with respect to 2. And that has been done over here. So the first equilibrium equation is differentiated with respect to 1. So all the terms are partially differentiated with respect to 1. The second equation is partially differentiated with respect to 2. Now, after that, we add up the 2 equations, we sum them up, and we get 2 times sigma 1 2 sigma 1 comma 2 is equal to sigma 2 comma 1 because we are dealing with a continuum. So adding these two, so sigma 1 1 comma 1 1 plus sigma 2 2 comma 2 2 plus the x1 body force comma x1 comma x1 and x2 body force comma 2. So these will stay on the right hand side, and the first these two are taken to the left hand side, and therefore negative comes. This is actually the value of minus 2 sigma 1 2 comma 1 2 in our compatibility equation. We can plug the value of 2 sigma 1 2 comma 1 2 into the compatibility equation. We get the final equation, which is sigma 1 1 plus sigma 2 2, the whole bracket, comma 1 1. So which means to say that each term has to be partially differentiated twice with respect to x1. Then the second small bracket has got again sigma 1 1 plus sigma 2 2, and there is a comma 2 2. So the term has to be partially differentiated twice with respect to x2. The right hand side has got minus 1 by omega. The body force x1 partially differentiated with respect to x1, and body force x2 partially differentiated with respect to x2. And that is actually the compatibility equation in terms of stresses. So this is applicable for both plane stress and plane strain, provided we use appropriate omega. Now, let us have a brief discussion about the other remaining 5 compatibility equations. We can see that in the case of plane strain, they will automatically become zero, all of them. And let's see how that would be. Now, in the case of plane strain, we have epsilon 33 equal to 0. So the second compatibility equation will have epsilon 33 equal to 0 and epsilon 23 equal to 0. So we already discussed that all the strains corresponding to the direction 3 are equal to 0. Because of equilibrium, the 3-2 and 3-1 strain will also be equal to 0. And that will make equation B equal to 0. So we will end up with strain 2-2 partially differentiated twice with respect to x3 equal to 0. And that makes sense because strain 2-2 will not be dependent on the variable x3. So automatically the second equation is satisfied. In equation C, again the same story, epsilon 33 equal to 0. So this second term is 0, 1,3 is equal to 0, and our epsilon 1,1 is independent of anything happening in the x3 direction, and that's what we assume in our plane strain. Again, equation C is 0. The other equation, again applying plane strain, so we have epsilon 33 equal to 0, so right hand side equal to 0. Epsilon 1,3, again this one is 0, this one is 0. We are left with epsilon 1,2, which we assume is again not dependent on x3, and hence all the terms are equal to 0. Similarly, the fifth equation has epsilon 2,3 term equal to 0, epsilon 1,3 term equal to 0, and epsilon 1,2 is independent of x3, so that is also equal to 0, and epsilon 1,1 by partial x2 partial x3, that comes out to be 0. Again, epsilon 1,1 by partial x2, we assume will not change if we apply any change in x3 direction, so this term is also essentially equal to 0. The same argument about the final equation, which has got epsilon 2,2 partially differentiated first with respect to x1 and then with respect to x3. So that term is 0 because epsilon 2,2 is independent of anything happening in x3, makes it 0. And on the left hand side, we have got epsilon 2,3 equal to 0 for plane strain. 1,2 is not changing with x3, so this one goes, and the first term epsilon 1,3 is 0 right from the get-go, so this term is automatically 0. So that tells us that in case of plane strain, all of them are satisfied. This type of assumption has to be appreciated, because if we are applying plane stress or plane strain, or we are opting for plane stress or plane strain in finite element analysis, we must make sure that our structure is obeying all of these conditions. Now let us quickly discuss about the plane stress problem, the compatibility equation for the plane stress. So as we said, the first equation of compatibility is the same. So we have already derived our equation. This one is applicable for plane stress. The equation B till F, equation F, they need some further discussion. Now the plane stress problem has got one issue, and that is that the strain 33 is a function of x1 and x2. So we have to enforce compatibility in the case of plane stress. We won't get automatically all the equations B till F equal to 0. And we will end up with some error, but we accept that error, and normally experience shows that it doesn't make much difference. So in plane stress problem, we again assume that epsilon 22 is independent of the change happening in x3 direction. So the first term comes out to be 0, and the term at the right hand side, which is epsilon 23, partially differentiated first with respect to x3 and then x2, that is also 0, because the second term, epsilon 33, partially differentiated twice with respect to x2, is not 0 in the case of plane stress, and we make it forcefully 0. Why is this not equal to 0? As we discussed, that epsilon 33 is a function of x1 and x2. So if this is made 0, then this term will be equal to 0. So it is rather enforced. We assume that this is 0. In the end, it might not come out to be 0, but we ignore it. So that is an important distinction between plane stress and plane strain compatibility. We can use the same argument in case of equation C when we are applying it on plane stress problems. We have epsilon 1 not changing with x3, so therefore the first term is 0. The second term is enforced, i.e. the second term is forcefully made 0, so and we will get the right hand side equal to 0. So again, it is enforced. In the case of shear equations of compatibility, we apply the same logic. Epsilon 33 is a function of x1 and x2, so therefore this term is not 0. We have to force it to 0. Then 1,3 is considered independent of x2, so that is 0. Epsilon 2,3 is considered independent of x1, that comes out to be 0, and epsilon 1,2 is considered independent of x3, and that comes out to be 0. The fifth equation has got epsilon 1 partially differentiated first with respect to x3 and then x2. We assume that this is independent of x3, so that comes out to be 0. And the 2,3s are independent of x1, so we assume that it is 0. Epsilon 1,2 is independent of anything happening in x3, so that is considered 0. And epsilon 1,3 has got nothing to do with x2, so that comes out to be 0. So that's how we use the same logic on the final equation, and we will get zeros. So essentially, the main takeaway in the case of compatibility is that in the case of plane strain, it is automatically enforced. So all the 6 equations become 0. The plane stress problems has got to be enforced. They will not automatically reduce to 0. So we push it, we force it to 0, and that induces some error in the plane stress problem, but that error is of smaller magnitude and it can normally be ignored. If we want to be more rigorous, then we will have to apply these equations and make sure that they are all satisfied. But it becomes a nightmare scenario to solve all these equations. They are highly restrictive, and it's just like doing no approximation and asking for a solution, a closed form solution, which in the case of complicated problems will be very challenging. That is the reason that we make use of computers, finite element analysis, such techniques to solve these type of problems, so that we don't have to work out analytical solutions. Now, final part of this presentation is to discuss the constants which we have used in our constitutive equations. So we have used different constants: mu's, g's, nu's, ease, all these constants, how to determine them? That is an important question which we should ask ourselves, because this material model has got all these constants. The rest is straightforward. So once we know these constants, we plug it in these in the material model, and we get our boundary value problem and solve it. So uh, everything follows straightly. But the main thing unknown is now the constants. So we will discuss three different types of tests just to give us some idea how to determine these constants. The first one is a hydrostatic compression test. Hydrostatic hydrostatic compression test is commonly used for soils, and it's also called as a one-dimensional consolidation test. It uses the instrument called odiometer and involve determining the consolidation and compressibility of soil specimens. For other materials like concrete, steel, it is not commonly used, but there is hydrostatic compression tests available for other material like concretes. They are not standard tests, nevertheless, they can be used. So essentially, what that test is, that we take an element of a specimen, so that can be a cube element taken out of concrete or cast in concrete, and then we apply hydrostatic force on it, equal force on it, and see where it crushes or work out its strength. So if we draw our P, mean hydrostatic stress, and the volumetric strain, if we draw a line, the bulk modulus can be worked out as the slope of that line. So although it sounds very simple, but this is a very involved test for materials other than soil. Sometimes this constant is called as B, bulk modulus, or K. That is equal to P by strain Kk. So strain Kk or strain V, whatever we want to call it, this is a volumetric strain, negative because of the compression, and that is equal to lambda plus 2 by 3 mu. So that is something which we already worked out. So we worked out our lambda, our P equal to lambda plus 2 mu by 3 epsilon V. So epsilon V is the volumetric strain, which is taken as epsilon Kk over here. So that is one test which will give us the bulk modulus. The other test is simple tension test. In this test, we can find out the Poisson ratio very straightforwardly. Epsilon 22 by epsilon 11 negative with a negative sign, or epsilon 33 by epsilon 11. So we have stress applied in one direction, and we are trying to find out our Poisson ratio. So that can be worked out. So that is a Poisson ratio, and the modulus of elasticity is stress by strain. So that is commonly known. Once we know E and nu, we can use the equation which we discussed previously and find out our mu and lambda. So two equations, two unknown, and we can find out our lambda. That is another test which can be used instead of hydrostatic compression test, and this is more straightforwardly used. This is commonly used to get our constants. Finally, we have a simple shear test to determine the modulus of rigidity. Again, the simple shear test is a test commonly performed on soil samples to determine their shear strength properties. This test involves applying a shear stress to a soil sample in a controlled manner while measuring the resulting deformation. So we have a shear box, we apply some loads on the box, and we try to fail the specimen in shear. For concrete or other material, this test is very challenging, but there are non-standard tests available for simple shear. So if we draw a shear stress strain curve, the slope of this will be the modulus of rigidity G, and that can be easily worked out. So these are the different types of tests. Some of them are standard, like simple tensions tests. Some of them are non-standard in case of concrete or other material, like hydrostatic compression test or a simple shear test. Now, this is a table which relates all these constants. So essentially, we have the modulus of elasticity E and nu, which is the Poisson ratio. If these two constants are known, then we can find out all the constants. So in this table, we have got shear modulus, Young modulus, E, constrained modulus, that's also sometimes used, bulk modulus, Lamé parameter, lambda, Poisson ratio. If we want all the constants in terms of shear modulus and Young modulus, then we can have the constrained modulus. This we haven't used, but also can be used in our calculation. We have bulk modulus in terms of shear modulus and Young modulus. We have got the Lamé parameters in terms of shear modulus and Young modulus, and similarly a Poisson ratio in terms of shear modulus and Young modulus. Similarly, if we know G, which is the shear modulus, and the constraint modulus, we can determine the rest of the constant in terms of these two. We know E and nu for most of the materials, so we can work out our shear modulus, which is E by 2, 1 plus nu, very well-known constant. Then we can work out our constraint modulus in terms of E and nu. We can find out the bulk modulus in terms of E and nu, Lamé's parameters. So E and nu for different materials is already known. So therefore, working out these constants from E and nu is not a problem. Thus, we finally conclude with this note that we can treat the different problems of structures as a boundary value problem. We can determine the governing differential equations. We have to apply the boundary conditions. Only the governing differential equation is not sufficient. Without boundary condition, the structure is unstable. So we can have a displacement boundary condition or force boundary condition. We call it traction. And traction is the force per unit area, which we call stress in our lower classes, but in advanced structure mechanics, traction are the forces on the face. When we say stress is actually a tensor having 9 components. So we can apply this model on any structure from simple to complex, and we can get all our unknowns. We have got 3 equilibrium equations. We have got 6 strain components or 6 strain expressions. We can plug the value of strains in the constitutive equation and correspondingly get 6 stress components. So 6 plus 6, 12, and 3 equilibrium 15. Those are the governing differential equations available. Now, the unknowns are 6 strain equations, 6 stress equations, and 3 displacements, U1, U2, U3 in the 3 direction. So those are unknowns. So 15 unknowns and 15 equations. So it's a determinate problem. As I said, only governing differential equations are not sufficient. We have to apply a boundary condition. And once we apply the boundary condition, we can have the whole analysis done.